In this lecture, I'm going to talk about an algebraic structure known as a ring, and we'll go into some definitions, basic concepts, and then state some examples. And then there'll be a second lecture on this topic that'll get into a little bit more of the details. A ring is an algebraic structure with two binary operations. We usually call them addition and multiplication, even though the operations are not necessarily what we think of as addition and multiplication of real numbers. Ring elements can be numbers such as integers, real or complex numbers, but they can also be other type of objects such as polynomials, square matrices, functions, and power series. And we'll look at a few of these examples in the latter part of this lesson. So more precisely, a ring is a non-empty set closed under two operations, which we call addition and multiplication, and that'll vary depending on the type of object we're dealing with. And then it has these following properties. So the addition operation is an abelian group. So we have embedded in our ring an abelian group, but then there's the multiplicative operation, which is not quite a group, but has some of the properties, which we'll see in a second. So the additive identity is labeled as 0. In terms of the multiplicative operation, it's associative. So we have that. We know it's closed. And there's also a multiplicative identity. And again, we call it 1, but it'll vary for these different examples. What's missing is the inverses. You don't necessarily have multiplicative inverses in a ring, and it doesn't have to be commutative either, although even a group doesn't need to be commutative in terms of multiplication. And then we have these distributive laws that relate the additive and multiplicative operations. They're just on the right and the left. So you could take A times B plus C and distribute it this way, or you can multiply A on the other side on the right and distribute it as shown here. If AB equals BA, and I'm just using juxtaposition to represent multiplication here, you'll see that often. I could have put in the asterisk here also. So if this is true, then you have a commutative ring. You still don't have a multiplicative group because of the issue with the inverses. A unit element of a ring is an element that has a multiplicative inverse. So an element U of a ring R is a unit if there exists V in R such that UV equals VU equals the multiplicative identity 1. The following theorem involves 3 basic results for rings. It may seem a bit tedious in terms of the proof, but keep in mind that this holds true for any structure that satisfies the ring property. So the idea is to prove it once for everything that satisfies a particular set of requirements, basically the ring definition, and then you don't need to do it multiple times. So let's have a look at the theorem. We have a ring with additive identity 0, multiplicative identity 1. We have these 3 properties. 0 times A equals 0 for every element in the ring. If minus A is the additive inverse of A, and that's the typical notation you would use, then the additive inverse of the multiplicative identity times the additive inverse of A equals A. And then third property is the additive inverse of the multiplicative identity times A equals the additive inverse of A. And I may say minus 1 and minus A as I go through this proof. I'll alternate between that and just saying the additive inverse of this or that. So let's look at the first one. We have, we'll start with this property here. This follows from a ring being an additive group, and 0 added to anything equals 0, including itself. So we have this. Then we multiply both sides of this by A. See that here. And then we use the distributive law on this. We get this here. Then since 0 times A is an element of our ring, it has an additive inverse, this thing here. Then we just add that to both sides. Adding it to this side, we get 0. Adding it to this side, we cancel one of these out, and then we get our result. Moving on to the second one, we have 0 times anything equals 0. So we'll multiply 0 times minus a, additive inverse of a. And then we can write 0 is this here. Any number, any element, I should say, of the ring plus its inverse equals 0 by definition. So we'll use the multiplicative identity. So that's going from here to here. That's what we've done. Then we multiply minus a times this using the distributive law. So we get minus 1 times minus a here. And then we just get 1 times minus a, but the multiplicative identity times anything is itself, so we get this here. Then we add a to both sides, to here and to this side. Of course, a plus 0 is a. Then adding a to this side cancels out the minus a, and we get this here, which is what we wanted to prove. Okay, now let's go to the third one. We'll make use of the second property, this here, and we'll multiply it by minus 1 to get what we have here. Then applying part 2 of the theorem, we have minus 1 times minus 1. We're just plugging in 1 for a. That equals 1. So this is 1. And then 1 times minus a, of course, is minus a. And then we don't touch the left side here, so we just get minus a equals minus 1 times a. The integers are a commutative ring. I'll leave it to you to check all the properties. The integer 0 is the additive identity, and the integer 1 is the multiplicative identity. Other than 1, no number has a multiplicative inverse. So I kind of stated generally here, but maybe give you a specific example. So for example, the multiplicative inverse of 2 is 1/2, but 1/2 is not an integer, so we fail there. It's only 1 that has the multiplicative inverse. However, we have this other property. If we have c times a and c times b, the only way this could be true for the integers is if a equals b, other than when, assuming c doesn't equal 0. So this property is known as multiplicative cancellation law, and that holds true for the integers. Another example are the integers modulo a prime number p under both addition and multiplication. That's a commutative ring. It's actually something called a field, which I'll get into in another lesson. A field is both an additive and a multiplicative group, and that's what we have here with the integers mod p, and it's usually represented here with this notation here. If we take the integers mod n, where n is not a prime number, under addition and multiplication, we still have a commutative ring. For example, Z6, which I went through in a previous lesson, is a commutative ring. In this case, we have what are called zero divisors. So two non-zero elements that multiply to 0. That's what defines a zero divisor, and I have an example here. So we have 2 times 3 is 6, so that's 0 mod 6. And we also have 2 times 0 is 0. So these two things are equal. And but what we don't have is 3 equals 0. In other words, if you tried to cancel the 2 out on both sides here, that would leave you with 3 equals 0. But that's false. So we don't have the cancellation law in this case here for the and when you don't have the cancellation law, you have what are called these zero divisors. A non-zero commutative ring with no zero divisors is known as an integral domain. There are several equivalent definitions. There's actually a list of them, and I'll give you a link to an article, online article, that goes through the different equivalent definitions. Some of them we haven't developed the terminology or the concepts yet to understand, but at least you'll have the list for further reference. So for example, the integers, which we talked about up here, are an integral domain, since we don't have zero divisors in that case. We mentioned zero divisors and multiplicative cancellation law, and it turns out the property of not, and I emphasize not here, not having zero divisors is equivalent to the multiplicative cancellation law. We can prove that going in both directions. So assume the cancellation law holds for a ring R, and suppose by way of contradiction that there exist non-zero elements A and B such that A times B equals 0. In other words, assume that we have zero divisors. Then by theorem 20 part I, we have that 0 times B equals 0. Then we have A times B equals 0, 0 times B equals 0. We can put that together. We have this here. And since we assume the cancellation law holds, we can cancel the B out on both sides of this, and we had A equals 0. But that contradicts our assumption here that we had non-zero elements A and B. So in other words, we've violated our assumption, and it must be that we do not have zero divisors. Going in the other direction, conversely, assume R does not have any zero divisors. So we want to show that it has this multiplicative cancellation law holds. So if we take this here, if we have C times A equals C times B, with C not equal to 0, and then we subtract one side from the other, done here, so that would equal 0, and then we can use the distributive law to go from here to here. And since we said C doesn't equal 0, and we have assumed no zero divisors, it must be that A minus B equals 0, and thus A equals B. And so we've shown that the cancellation law holds that we can cancel out the C's and get A equals B. Isomorphic rings are rings that have the same structural properties, even if their elements may be different. Formally, ring R was operations plus and star, and ring S, and I use different symbols here just to emphasize that the operations don't need to be the same. They just need to have an additive operation and a multiplicative operation. These two rings are isomorphic if there is a bijective function f between R and S, such that you have this property in terms of the addition, this property in terms of multiplication, and then you have the multiplicative identity preserving aspect this here. In other words, the multiplicative identity of R gets mapped to the multiplicative identity of S. On the other hand, a ring homomorphism only needs to satisfy these three properties. We saw this something very similar for the group homomorphisms, but it doesn't need to be a bijection. So it doesn't need to be one-to-one and onto. Several properties follow immediately from these assumptions here, and theorem 16, that was a theorem I proved for groups, basically stated what I just put here, that the zero identity, the additive identity in R gets mapped to the additive identity in S, and the additive inverse of A gets mapped to the inverse of f of A for every A in R. And there's quite a long list of properties. I won't go through them here, but I'll give you a reference to properties of ring homomorphism, which of course apply to ring isomorphism, since every homomorphism is also an isomorphism, but of course not the other way around. I have a couple of examples of isomorphisms and then something which can't be an isomorphism on this slide here. First example is take the ring R of real numbers. That's isomorphic to the ring of all 1 by 1 matrices R under matrix addition and multiplication, and the isomorphism just maps the real number into the matrix with a single entry. So not particularly interesting. A little bit more interesting is the ring of Cartesian product R cross R. So these are just tuples A, B in this set here. And the set of 2 by 2 diagonal matrices with entries from R. So the set of matrices that look like this was A and B from the real numbers, and then 0 off the main diagonal. And then the mapping would be to take A, comma B in R cross R and map it to this matrix here. Then an example of a non-isomorphic rings. Consider the polynomials with real coefficients and the ring of polynomials with complex coefficients. And let's assume that they are isomorphic, so there's some mapping here between the two. Then we have f of I, where I is the imaginary number, square root of minus 1. So it's an element from here. It's a polynomial, trivial polynomial. It's just a constant, but it's still a polynomial. And that gets has to be mapped to some element in the real numbers, right? We have that isomorphisms are bijections. So this must be true for some value a. Then if we take a squared, that equals f of I squared, and then from the properties of an isomorphism, f of I squared equals f of I times f of I, so you get this equality here. And then I squared is minus 1. That's the imaginary number square root of minus 1, so when you square it, you get minus 1. So now we have a squared equals f of minus 1. From the properties of ring homomorphisms, we have f of 1 equals 1, and we have f of minus 1 equals minus 1 as the added inverse of 1. And so we have a squared equals f of minus 1, which equals minus 1. We don't really need this here, I just mentioned that. But then, so we have this, but then no real number 1 squared equals minus 1. Thus we have a contradiction in our initial assumption that such an isomorphism exists is false, and therefore there is no possible isomorphism between the real and complex ring of polynomials. The set of polynomials with coefficients from the real numbers, which we denote Rx, is a commutative ring. For example, the following is an element of Rx. This should look familiar from high school algebra. In fact, it isn't any different from what you've seen in high school algebra. It's just that we're now classifying it as a commutative ring. Two polynomials are equal if their corresponding coefficients are equal. The additive identity is the real number 0. So you have a 0 equals 0, and then all the rest is just coefficients are all 0. Then the multiplicative identity is the real number 1. So in that case, a0 equals 1 and a1, a2, however many coefficients you have, they're all equal to 0. Addition is pairwise. We add each coefficient of like terms. We have the distributive law. I give an example here, or actually I kind of stated generally. If you have x, f of x, g of x, h of x, and you multiply f times the sum of h and g, you write it out like this. It's also true if you multiply on the right and you get something similar. Multiplication, again, this is something you should have seen in high school algebra. It's just a matter of multiplying each term here times each term here. So you multiply 2 times 1, 2 times the minus 2x, 2 times the 2x squared, and then 3x times each one of these, x squared times each one of these. And then you collect the terms with like powers of x, and you get this expression here, and then you just add the different coefficients together and you get your solution. Additive inverses are formed by taking the negative of each coefficient, so that's pretty simple, I think. Multiplicative inverses only exist for non-zero constant polynomials. So for example, this polynomial here, x cubed minus 5x plus 2, has this as its inverse, but this is not a member of the polynomials. And in fact, that gives us a reason for, or a good reason for why, a good motivation for why rings are defined as not necessarily having multiplicative inverses, because that would exclude very useful sets like the polynomials, which as we know from high school algebra, are very useful and come up in a lot of places, physics and elsewhere. Polynomials can also be defined over fields. In other words, the coefficients are over different fields other than the real numbers, for example, the complex numbers. And I'll point you to this article in Wikipedia on polynomial rings. It'll have a lot more information than I'm providing here. Take any set S and form the power set, and we'll have another example of a ring. The power set is a set of all possible subsets of our set S, including the empty set and the set itself. Over the elements of the power set of S, define addition to be symmetric difference, and I'll explain that down here. It's sometimes called exclusive or the XOR, and multiplication to be intersection. The symmetric difference of sets A and B is a collection of elements in either A or B, but not in both. We write it like this: A triangle B. The symmetric difference can also be expressed as the union of two sets minus their intersection. So in other words, what's in either set A or B, but not in both. And the intersection of sets A and B is the collection of elements in both A and B. So I'm sure you've seen that before. The power set with the above operations is a commutative ring. Clearly, intersection and symmetric difference result in another subset of S, and thus we have additive and multiplicative closure. The additive identity is the empty set. The additive inverse of a set A is itself. Symmetric difference is commutative and associative. The multiplicative identity is S. S has only S has a multiplicative inverse. That's okay. We don't need to have that for a ring, at least not for every element. Intersection is commutative and associative. Intersection distributes over the symmetric difference. That's a little bit hard to see, so I'm just stating this here, but that's something you need to actually work out, but I didn't provide the details. Since the cancellation law does not hold for intersection, the power set of a set S under the stated binary operations is not an integral domain. Okay, so I've stated a few things here without proof. You may want to look into proving some of those things on your own, but main point here was just give you another example of a commutative ring. On this slide and the next, I have another example of a ring. It's the set R, where you have A plus B times the square root of D, and A and B vary over the integers, plus or minus, and D is a fixed element that's a positive integer, like the square root of 2 or the square root of 5 and so forth. And this set is denoted by this notation here. To reduce the elements of R to their simplest form, we require that D be square free, so none of its factors can be a square. 24 would be square free. 90 is not, because you have 3 squared as one of the factors. And you can see why that you want to not allow for this, because when you take the square root of 90, you're going to get the square root of 10 times 3, and then the 3 just becomes part of the b, and you're getting redundant. elements in your set, your possible sets here. So to show that R is a commutative ring, we can go through the steps. Addition is just you add the A's together and then the B's together like this. This is just standard addition of real numbers. The additive identity is 0. Additive associativity and commutativity are inherited from the real numbers. The additive inverse is just a negation. Then you can multiply just the way you would do from high school algebra. This is very reminiscent of how you multiply complex numbers also. So we have multiplicative closure. Multiplicative associativity and commutativity are inherited from the real numbers. The multiplicative identity is 1. Since 1 equals 0, 1 plus 0 times the square root of d. And the distributive laws carry over from the real number. So we have a commutative ring. There's a few shortcomings related to this ring, but I'll mention those on the next slide. So there are a couple of issues with this ring. One is the inverses don't normally exist. The inverse of a plus b square root of d, went over that. It's fine. It exists in the set of real numbers, but not in this set that we've defined here. At least not normally. So if you take this and you multiply by 1 in the form of this fraction here, you notice that numerator and denominator are the same. And you multiply that out and you get this term here, which is not normally an element of our set R unless a over the denominator, this thing here, is an integer, and then minus b over this is an integer. So that's not normally the case. So you don't usually have multiplicative inverses. Then the other problem is you don't have unique factorization. So if you take minus 4, you can write it as 2 times minus 2, but you can also write it as 1 plus the square root of 5 times 1 minus the square root of 5. You notice you get 1, then the square root of 5 minus square root of 5 cancel, and you get a minus 5, and that gives you minus 4. So there's two ways of factoring minus 4. There's ways of fixing this that are fairly complex that get you into various conditions on the value of d, which I'm not going to get into here, but I'll just mention that. We have a few more examples of rings that are matrices. If we start with a set R that's a ring, and then we form these different matrices, which I'll go over in a second, then you also have a ring. So the first one is the set of n by n matrices over R, in other words, elements from this ring R, denoted by m sum n of R. That's a ring. It's sometimes called the full ring of n by n matrices. The set of upper triangular matrices over R, and I give an example here, I'll say R is the integers, then if you have all the matrices of this form here, where everything below the main diagonal are 0, and then the things on the main diagonal or above may or may not be 0, that's a ring. Then you can have sort of the opposite of this, where you have zeros above the main diagonal and 0 or non-zero elements on the main diagonal or below. That gives you a ring. And then if you just have elements from R on the main diagonal and zeros everywhere else, that's also gives you a ring. Okay, so that's the final slide in this lesson. I have another lesson on rings, and then I'll follow up with some lessons on fields.